Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study lecture on measurement of position. As usual, before we enter the study of today's lecture, let's have a quick overview about the answer to these 4 common questions that you may have in mind. Question number 1, why to study this course? Question number 2, how to study this course? Question number 3, what are you going to study in this course? And question number 4, how to learn the knowledge in this course. Let's begin with the overview about the answer to the first common question, which is about why to study this course. The answer should be, number 1, human beings' mission on Earth is to understand the world. Then how to understand the world? The answer is to discover the knowledge in the physical world. Then how to discover knowledge in the physical world? The answer is to make use of sensory data. Then how to obtain sensory data? The answer is to use measurement and the sensing system. All right. The second reason is because we want to improve or change the world. All right, so this is another mission of a human being on Earth. Then how to improve or change the physical world? The answer is to invent smart systems, smart product, smart machine. Then how to invent smart systems, smart products, smart machine? The answer is to incorporate closed loop feedback control system inside these system, machine, or product. All right. Then how to develop a closed loop feedback control system? The answer is to make use of measurement and the sensing system to provide the sensory data. All right. Then from this slide, you will see we have smart parking system, smart street light system, smart building system, smart home system, smart environmental system, smart health system. And you also see the Internet of Things, and inside the Internet of Things, the 2 basic devices include sensor. Therefore, this course is extremely important, not only for application in industry, but also for many applications in society. The second common question that you may have in mind is about how to study this course. All right. My recommendation to you is to put yourself into the mindset of a designer. Then in this way, with the keyword of design or designer, automatically you want to know the answer to these 4 questions. Who are the user? What are the need of the user? What are the functionality of your future product or system, which could meet the need of this user? And what should be the solution behind the design of your future product or system, right? The answer to the first question should be obvious to you. The user include human being who want to understand the world. The user also include smart system, smart product, and smart machine, which need to have a sensor in order to provide sensory data, right? Then what are the need of this user? The generic need is to have sensory data, right? Then what should be the functionality of the product or system that you are going to develop in order to meet the need of this user? So the answer depends on the specific user with the specific need. For example, smart vehicle may need certain type of a sensor. Smart robot may need another set of sensor or measuring system. So therefore, their need may not be exactly the same, right? The way to answer question number 3 depends on the specific user and their specific need, all right? Then what should be the answer to question number 4? The answer should be the study of this course. At the end of the study of this course, you should be able to know the solution behind the design of your future system or future product, which could be sensor or Internet of Sense or Internet of Sensor, etc. Right? Then the third common question that you may have in mind is about what are you going to study from this course. Basically, this course covers the physical principle behind the design of a popular sensor in the domain of electronics, in the domain of mechanic system, and also in the domain of environmental system, and in the domain of intelligence system. All right. In addition, this course covers the basic detail about the physical world, the basic detail about the conceptual world. The course also covers the basic knowledge for you to apply in order to cope with randomness in the physical world, and also the basic knowledge for you to apply in order to deal with the fuzziness in the conceptual world. All right. Then the fourth common question that you may have in mind is about how to apply knowledge learned from this course. And this slide basically shows you the general guideline for the design of a sensor or sensing system. And the design of a sensor and the sensing system involve 2 steps. Step number 1 is to design the sensing element which will transform the value of the physical quantity on the measurement into readable value. The second step is to calibrate, okay, the sensing and the measurement system so that the output from the sensor is exactly equal to the input of value of the physical quantity on the measurement. All right. In addition, after calibration, you should be able to assign, okay, the unit of a measurement to the output, which will be exactly equal to the unit of a measurement at the input of your measurement and the sensing system. All right. For the first step, you may face 2 situations. The first situation corresponds to the case in which the use of a front-end sensing element should be good enough for you to achieve the transformation from the value of physical quantity into readable value. And in most cases, you may face this second situation in which you have to make use of a front-end sensing element plus back-end sensing element in order to transform, okay, the value of a physical quantity on the measurement into readable value. All right. So this slide basically gives you the general guideline so that by following this guideline, you should be able to apply learn the knowledge in this course. Now we enter the study of today's lecture, which is about the measurement of position. All right. So let's first look at the physics or basic detail about the position. And first of all, we may want to know, okay, why is it important for us to consider this physical quantity, right? The answer will be position are extremely important, not only for human being, but also for machine, right? So this video shows you the application with the knowledge about the position in order to achieve, okay, autonomous navigation for land vehicle. So you will see we have a camera, we have a laser rangefinder. The laser rangefinder basically is a measurement of distance. Okay. And the camera is here. We will study the detail about the camera in a separate lecture. So we can use camera to capture image, then we process the image, all right? Then we identify the area in which there may be presence of obstacle. Then we use this information to guide the scanning with laser beam, right, in order to obtain distance information. Then we can make use of such information to automate the task of object tracking, target tracking, or autonomous control of the car following. Okay, so this is one typical scenario in which the knowledge about the position play very, very important role, all right? And this video showing you the industrial application in the production line in which a robot will undertake autonomous pick and place. And then you will see for such behavior, knowledge about the position is critical, all right? And in this video, then you will see again that the knowledge about the position is extremely critical to implement such autonomous behavior, which could be performed by humanoid robots. All right. And you know, okay, so in the physical world, all the entity subject to spatial constraint and the time constraint, okay? So therefore, we want to know, okay, the position and also the time associated to all the physical entity in the physical world, all right? So space and time are the background, okay, knowledge about the existence of any entity in the physical world, all right? And in order to tell the value for spatial property, we need to have a reference. In other words, in order to tell the position, so we must provide the reference. For example, distance means what? Distance means a relative position with respect to a reference point, all right? So we can talk about distance between 2 points, okay? Or distance of 1 point with respect to another point. So therefore, we need to have a reference. So therefore, for space and for time, we need to have a reference for space, reference for time. Okay, then what should be the solution for us to provide the reference? All right. So in mathematics, we know that we make use of axes, okay, to represent the reference, okay, for space or reference for time or reference for any other physical quantity. All right. Then what is the axis? So axis consists of origin, direction, and deviation or scale. Right. So therefore, from the need to understand the spatial constraint or the need to understand the time constraint, automatically we need to introduce reference for space, reference for time, all right, in order to tell the information about the position of physical entity in the physical world, all right. Then here is an example of reference for time, because time is a scalar, so it's a one-dimensional value. We just need to have a single reference. It should be good enough. So we have an origin, we have a direction. Time is always increasing, okay? And also the division or scale in terms of a second, minute, hour, day, week, etc. All right. Then for space, we know that we are living in a three-dimensional space, okay? In some situation, we may just consider reference, okay, along a single direction. And sometimes we may want to know or have a reference for a planar surface. And in general, we want to have a reference for three-dimensional space, all right? So if we only consider or just restrict our study within one-dimensional space, then in this case, we just need to have a single reference or single axis in which we have an origin, we have a direction, we have a deviation or scale, right? If we want to study the position or motion, okay, in a planar surface or in a two-dimensional space, then we need to have two reference in two different directions, okay? One in the horizontal direction, another in the vertical direction. Then in this case, we have two reference, and each reference correspond to one axis, okay? Then we can make the origin of these two axes to be superimposed together, all right? Just to simplify the notation, all right? Then in the case of study in the three-dimensional space, then we need to have three reference, okay? And each reference will have one axis. Then in this case, we will have three axes, okay? Then we can make these three origin of these three axes to be superimposed at the common point. So this is why we have a common origin, all right? Then however, the direction of these three axes are orthogonal, right? Then each axis has its division and the scale, right? Then with each reference, okay, or each axis, then we can tell the position. And the position basically means the distance between origin and the point, okay, on the point of the object on the reference, all right? So then this distance is called as a coordinate. So in technical term, so a coordinate basically is the distance between the origin and the point along an axis. And then this point could be the projection of the object of any physical entity onto the axis of a reference, all right? So then the distance has a unit of a measurement. The unit of measurement is indicated by the unit of a measurement of a scale or deviation, all right? So this is the detail about the reference for space, reference for time, all right? Then for example, we have this reference for time, and each division corresponds to 1 second, all right? Now we want to know what is the time correspond to point A, what is the time correspond to point B. Let me just count the number of the division, then the answer will be time for A is 16 seconds, time for B is 27 seconds. That's it, all right? Then in the two-dimensional space, for example, we have a two reference, okay, or two axes, okay, and their origin are superimposed together. Then in this case, we must have two distance, right? Distance to origin along horizontal axis, distance to origin along the vertical axis, all right? Then these two distance are called as the x coordinate and the y coordinate, right? Then for example, what should be the x coordinate of point A? Then you will see the distance from A to origin along the x-axis should be 1, 2, 3. Then distance from A to origin along the y-axis should be 1, 2. So therefore, coordinate of point A should be 3, 2 meter, right? Then what should be the coordinate for point B? Then you see distance from B to origin along the x-axis should be 1, 2, 3, 4, 5, 6. All right. Then distance from origin to point B along the vertical direction should be, or vertical axis should be 1, 2, 3, 4, 5. Therefore, the coordinate of a point B should be 6, 5 meter. Right. So this is a way for us to describe the detail of a location. All right. Then if we follow this background knowledge, then everyone will understand our description of a position. All right. And besides the XYZ coordinate, we may also use the polar coordinate. And the polar coordinate is suitable for us to describe the output from radar, from laser rangefinder, because laser rangefinder just scan in the horizontal plane. Then at every angular position, then you will measure the distance from the sensor to the target point. So therefore, the output should be the angular position plus the distance, right? If we put these two information together, then we call them as a polar coordinate, right? So it's quite straightforward. So polar coordinate consists of a distance from origin to the point on the measurement plus angular position, okay, of this vector from the origin to the point on the measurement, right? So r theta. So mathematically, we could undertake, okay, conversion between polar coordinate and the XYZ coordinate, right? For example, we know the XY coordinate of point A, then what should be the distance from origin to point A? Answer is the square root 3 square plus 2 square, all right? Then what should be the angle between the vector from origin to point A and the horizontal x-axis? Then the answer should be inverse of a tension function, which is equal to the ratio between y coordinate and the x coordinate. So y coordinate equal to 2, x coordinate is equal to 3, all right? And for point B, if let's say we know the xy coordinate of a point B, then what should be the polar coordinate of a point B? So the answer is distance from origin to point B equal to square root 6 square plus 5 square, right? Then the angle between vector from origin to point B and the horizontal axis should be equal to inverse tension, okay? And the tension is equal the ratio between y coordinate of a point B and the x coordinate of a point B. Then we have a 5 over 6, all right? So these are the simple calculation for us to do the conversion, okay? So once we know the coordinate, we know what is a reference, we know what is a axis, etc. Then we are ready to define position, right? Position basically refer to the coordinate of a point, all right? And the coordinate of a point could form a vector in mathematics, all right? And since reference for position in the three-dimensional space involve the use of 3 axes. Therefore, we have 3 references, okay? One for X, one for Y, one for Z. Therefore, we can call them as a system, all right? This is why we call them as a coordinate system or reference system, right? So automatically, we know, okay? So reference for space actually is a system, because on the normal situation, inside a reference, there are more than one axis, all right? Then inside the coordinate system, then we can use a vector to represent a position in general, all right? For example, in the three-dimensional space, we have a global coordinate system. Then for each rigid body inside the physical world, we could define a position vector. And there is a background knowledge. This is a convention in the study of a mechanical system. We normally assign a local coordinate system to each rigid body. Therefore, the position of the rigid body is equal to the position vector of the origin of the local coordinate system with respect to the global coordinate system, all right? Because we assign a local coordinate system to each rigid body. Then the origin of the local coordinate system represents the position of that rigid body, right? So this is a convention used in the study of a mechanical system, all right? Okay, so that's about the detail, okay, of position. Okay, so we can talk about the position in the time axis, position in the space axis, all right? And in the three-dimensional space, normally we have three axes, okay? And the position could be represented by a vector, all right? So these are the detail about the position of entity in the physical world. Then next question should be how to indirectly measure the position of a physical entity, or how to directly measure position of a physical entity in the physical world, all right? So we look at the scenario of doing indirect measurement, and the indirect measurement means computation with the knowledge about the related physical quantity, okay? For whatever reason, for example, we are able to measure the related physical quantity, then how to use this knowledge to compute position, all right? So this corresponds to this scenario of indirect measurement, all right? Based on our knowledge about the physics and also our knowledge in mathematics, we can formulate these four observations, okay? In physics, everyone should know that the position could be calculated from the knowledge about the velocity. Position could also be calculated from the knowledge about the acceleration. All right, in year one physics, we have studied this relationship among position, velocity, and the acceleration. All right. Then in mathematics, we also know that we should be able to determine the position of a point in a two-dimensional space if we know the distance from this point to a few reference point, all right? And similarly, in a three-dimensional space, we should be able to determine the position of a point if we know the relative distance from this point to other reference point, all right? So these are the two scenarios for us to use in order to calculate, okay, the value for position. Now I'm going to show you the detail for each of these four scenarios, right? For example, we could consider this special case of velocity. For example, we know that the velocity of a moving object is constant, or velocity of a moving signal is a constant. Then how to leverage on the knowledge, okay, of this situation in order to calculate position information, all right? So in the first case, you see, okay, if object move along the x-axis, for example, okay, with a constant velocity, then what should be the time function for us to use in order to calculate its position at any point of time? The answer is what? Straightforward, okay? Xt equal to initial position plus increment of position due to constant velocity. So it's v times t. So this is very simple equation. Immediately you know, okay, once we know V, then we can calculate position at any point of time. Okay, so that is straightforward. All right, but here we will pay attention to this particular situation. Now we know the velocity of the signal. For example, the light, the speed of light is a constant, and the electromagnetic wave are light. Okay, so therefore the speed of electromagnetic wave is a constant. All right, so how to leverage on this knowledge? Okay, so the answer is to leverage on this property in order to come out the solution. Okay, so that we can indirectly compute, okay, or measure the position of a moving object, and later on we'll show you the detail. All right, so this is the first scenario, which corresponds to the case in which velocity is a constant. So we can explore such a special case, all right, in order to come out the design of a different type of a product, and in particular, okay, make use of this property of signal which travel at a constant velocity. All right. Second scenario corresponds to the special motion in which the acceleration is constant. Okay, and for example, the gravitational acceleration on Earth is constant, and we may have other situation in which if the applied force is a constant, then the induced or the acceleration may be a constant. All right, so we can leverage on the use of this type of information. Then in physics, we know, okay, if an object undergo a motion along the y-axis, okay, with a constant acceleration a, by default, in this case, if y-axis is vertical, then a equal to g, which is a gravitational acceleration. All right, okay. So from the study of physics, we know that the y coordinate as a function of time t, it should be equal to initial y coordinate plus increment of a coordinate y due to initial velocity v0 plus increment of y coordinate due to constant acceleration 1/2 a t squared. So this is due to, this is the increment of y coordinate due to constant acceleration. So it's quite straightforward. All right, so immediately we have an equation for us to calculate the position, okay, along y-axis. Then come to this question, okay, how to explore this knowledge, let's say explore the use of signals velocity, which is a constant, in order to come out the product or system for the measurement or indirect measurement of the position. Okay, so the answer should be similar to this question: how to determine position from a distance? Because we are able to determine distance from the velocity, constant velocity of a signal. Okay, later on I will show you, okay, how to determine distance from signals constant velocity. All right, so first look at the answer to this question. All right, so how to determine position from distance. All right, in case if let's say we only know one distance from a physical entity, okay, to a reference point, okay, then in this case we only know that this physical entity should be on any location on the surface of a sphere centered at the reference point. Okay, and here the reference point basically means is an emitter of a time signal. So let's say we have an emitter of a time signal, then the object or any physical entity will carry a receiver of a time signal. Once he receives this signal, then we calculate the sending time and the receiving time, then theta t times speed of the light, then we know this distance. All right, so in case if we only know one distance, then we only know that this object is on any point on the surface of a sphere, right? If we have two measurement about the distance, that means distance from this object or this entity or this target to two reference location, then we can draw two spheres. Then two spheres will intersect in space, okay, along this circular path, the circle. Intersection between two spheres should be a circle. Then this object will be at any location on this circle. All right. Then how's about the this situation? We know the distance from the target to 3 reference points, right? Then in this case, we can introduce a third sphere. That's the third sphere will intersect with this circle at the 2 points. So then in this case, we narrow down the solution to one of these 2 points. Then how to decide which one is the correct one? Then we still need to have one extra condition, okay? So one way to introduce extra constraint is to limit the motion of this target on the planar surface, okay? We know that this object only have 2 coordinates because the third one is equal to 0. Then in this case, with 3 reference point or 3 emitter of a time signal should be good enough, all right? And the second way to introduce extra constraint is to add in the 4th reference point. So then in this case, we know the distance from the target to 4 reference points. Then in this case, we should be able to narrow down the solution to a single location, right? So this should be the working principle for us to determine position from a distance, all right? Then next question you may ask, how to determine distance, all right? The answer will be to use time signal emitter and the receiver. For example, we have a receiver which will be carried by robot, by smart vehicle, by person, whatever, all right? Or by any target, all right? And we have an emitter at the known position. That means their position, the position of this emitter are known in advance. And also, we let emitter to send the time information, okay, to the receiver, because this electromagnetic wave could be encoded with 0101 binary number, all right? So inside the binary number, we can write in XYZ coordinate value plus sending time, all right? And here we assume all the emitter and the receiver have the same clock, very, very precise clock. So we call them as atomic clock or something like that, okay? So very, very precise, all right? Then once the receiver receives the signal, then you can detect what is receiving time. So then theta t should be equal to receiving time minus sending time, okay? Once we know the time difference, then this time difference times the speed of light will give us the distance between one pair of receiver and the emitter. Then in this scenario, you see we have a 3 pair of receiver and the emitter, okay? Because this receiver could form a 3 pair with these 3 emitters, right? So let's answer this question of how to determine distance, okay? Between 2 locations, all right? Then, okay, so we are ready to come out the solution for us to calculate, for example, position in a 2-dimensional space from the knowledge about the 3 distance, right? So then in this case, assume in the 3D space, we have 3 emitters placed at the A, B, C, and each emitter will send the information such as X coordinate, Y coordinate, and the sending time, right? X coordinate, Y coordinate, and the sending time, X coordinate, Y coordinate, and the sending time. Then receiver will receive this information plus the receiving time, because inside the receiver, there's also atomic clock, okay? Because they are running at the same time. So therefore, we will know what is the receiving time. Then we will know what is the distance, all right? Then with this distance, it should be good enough for us to come out the solution for the calculation of a position, okay? Then here, we have the detail of equation. Okay, for example, we should be able to write down the circle center at the point A, the equation of a circle center at the point B, the equation of a circle center at the point C, and the radian for circle at the point A should be equal to velocity times theta t, and the radian of a circle at the point B should be equal to velocity times theta t. All right. So in this case, theta t is equal to t b prime minus tb. So this one is the receiving time. This is the sending time. Right. Similarly, for the circle center at the point C, we could write down this equation. Right. Then we expand these three equations. Then we let the first equation to be minus out by the second equation. In this way, we will cancel out the x squared, y squared. Okay, and then we obtain this equation. Similarly, we let the first equation to be minus out by the third equation. In this way, we cancel out the x squared, y squared. Then we have this second equation here. Now we can put these two equations together into a matrix equation. Then we compute the inverse of matrix. Then in this way, we will obtain the solution for us to calculate x, y, right? And here, A is a coefficient matrix with all the coefficient in front of x and y. B is a coefficient vector, okay? So B contains this value and this value, all right? So this is a quite straightforward solution, all right? Then this exercise is for you to think about or to do at home. The question is, what happens if we have more than 3 emitter? Then what should be the solution? All right, so you try to come out the solution for this scenario. All right, and this video showing you implementation of this solution by a company. You see, we can compute the location in a 2D space, okay, in real time. And in this case, we only consider the XY coordinate of the geometry. Okay, we ignore the height of the geometry. So you see the accuracy is quite accurate, right? In this case, also we are in a 3-dimensional space, but we only care about the XY coordinate. So you will see the procedure about how to install the software, how to do the setup. Then you see, okay, they place the emitter at the fixed location or at the location in which the coordinate XY are known in advance. Since the XY coordinate of these four emitters are known in advance, therefore we can visualize their location, all right? The fifth one should be the receiver, okay, on the target, a moving target, right? The blue color one should be the receiver, okay, which is placed on the moving target. So this is the one, right? So you see, when we move this receiver, the XY coordinate of this receiver could be calculated in real time, very, very precisely. All right, so you see this principle which has been implemented, okay, with a real product. All right, so now we move on to consider the situation in which we would like to know XYZ coordinate instead of XY coordinate. All right, then in this case, instead of having 3 emitters, we need to have 4 emitters. All right, so this is a scenario correspond to the GPS inside your smart handphone or GPS inside your smart vehicle, etc. Right? Then what should be the equation behind the calculation of making use of GPS in order to determine XYZ coordinate of a moving target? All right. So then the equation should come from the 4 equation of 4 sphere, because we have 4 emitter. Okay, so emitter 1, emitter 2, emitter 3, emitter 4. Each emitter has their own precise XYZ coordinate, and each emitter, okay, will send out the time signal with the sending time. Then the receiver will receive this signal. Then the receiver should be able to calculate the data t. Then data t times speed of light should be the distance from the receiver to this emitter. Therefore, center at this emitter, we should be able to write down the equation of a sphere. Then this is the equation of the first sphere, equation of the second sphere, equation of a third sphere, equation of the fourth sphere, right? Then from these 4 equations of a sphere, we let the first equation to be minus out by the second equation. Then we should be able to remove the term, okay, of x squared, y squared, z squared. Then we have this linear equation for x, y, z. Then we let the first equation to be minus out by the third equation. Then we have the second equation. Let the first equation to be minus out by the fourth equation here. Then we obtain this third equation, all right? Then we can put these 3 equations together into a matrix equation, all right? And put them together and to form this matrix equation. Then we'll see this is a 3 by 3 matrix. Then this is a 3 by 1 vector, right? And this is a square matrix. Then we can compute the inverse of this square matrix. Then immediately we have a formula for us to calculate x, y, z. All right, so it's quite straightforward. All right, and this is an exercise for you to do at home. Okay, what happens if, let's say, we have a receiver which could receive a signal, okay, more than 4 emitter. Normally it's true, inside our smart handphone, our GPS receiver could receive a signal or 12 signal, etc. Then in this case, what should be the solution for us to calculate X, Y, Z? All right. And this picture basically showing you that inside your smart handphone, okay? So you have the built-in GPS receiver, okay? And automatically the software will help you to calculate what is your actual location, all right? And the display on the map, so you know what is your position, okay? With respect to a global coordinate system, all right? So that's about the basics of indirectly determine the position, okay, in the 1-dimensional space, 2-dimensional space, and the 3-dimensional space, all right? But our focus here is on direct measurement of the position. Then you may want to know what should be the physical principle for us to follow in order to guide the design of our own measurement and the sensing system for position, all right? So here, we can state these 2 observations. The first observation is known to you because in the previous lecture, we have already leveraged on this observation in which the statement is to say that all microcontrollers are programmable sensor of DC voltage, all right? So we consider this observation as the design principle 1. In addition, all microcontrollers are programmable sensor of the digital signal. For example, if for whatever reason we are able to convert the value of a physical quantity on the measurement into digital signal in the pulse waveform, then microcontroller is ready for you to count or to use in order to count the number of a pulse, all right? Or to have to derive the signal of starting the counting window and the ending of the counting window. Then in between, you can use microcontroller's self-internal pulse to do the counting. So you have 2 scenarios. Okay, one is to use a digital signal to serve as a clock signal to do the counting, or to use digital signal from external physical quantity to serve as a time window. So you have a start time for the counting and the end time of the counting. Then microcontroller use is internal clock to do the counting. Right, so these are the 2 scenarios. So these are the additional, okay, observation for you to know. Now you will see it is extremely important for you to study this course MA4822, which is about the microprocessor system, right? Because this course could leverage on the property or capability of a microcontroller to facilitate the development or design or implementation of a measurement and the sensing system. All right. So now I'm going to show you the example which will make use of design principle 1 and the design principle 2. All right. By following the example, then you should be able to come out with your own solution. Okay. So principle number 1 is to consider okay, microcontroller as a sensor of DC voltage. Then in this case, you just need to know how to transform position into voltage, right? If you are able to do that, then you have a solution already, all right? Then the design solution should be this one, okay? Because inside microcontroller, we have this module such as a voltage synthesizer, analog comparator, digital counter, digital display, right? And the working principle, you know, okay? Because we predict the digital value for voltage and use the predicted value to synthesize DC voltage, and use the synthesized DC voltage to do comparison with the input voltage. When the value match, then we will stop the counting. Then the actual value inside the counter should be the digital value, which correspond to the analog input here. All right. Then all the problem become how to transform the value of a physical quantity on the measurement into DC voltage. Okay. Then in this case, how to do position voltage conversion. If you have an answer, then you have an answer to this question of how to apply, okay, principle 1 to design, okay, digital measurement and the sensing system for position, right? So actually, there are many ways for us to do the conversion from position to DC voltage. And for example, this is also a popular solution, okay? So we call this sensor as an infrared distance sensor, right? So we have infrared emitter, LED, then we have a light detector, which is called photo transistor or photodiode, all right? So then the light will propagate in the space, hit the target, then reflect back, okay? So the amount of energy received by the photo transistor will be reflected by the voltage as output here, because the light will transmit out, then bounce back, will hit the photoresistor, okay? Then this one will will produce a response like in terms of DC voltage as output, and this one is proportional to the amount of energy received by the gate pin here, all right? So if there are more energy received here, then the current, you will have a more current which will flow through here, okay? Then the voltage will drop, all right? Okay, so and then the input-output relationship will looks like this, right? So this is the output voltage, and this is the distance to reflective object. So you will see we have infrared transmitter and the photodiode to detect the angle, the reflected energy. All right. So when the distance increase, the amount of energy will reduce. All right. So, and here you must pay attention. So there is a area for the measurement. Okay. So you will see there is a linear relationship between the distance and the voltage. All right. So this is a very, very short range, like between 0 centimeter to 5 centimeter, roughly, okay, in that area. Okay. So by doing calibration, we can easily ignore this measurement range. Okay. Or you can implement a decision rule to know, okay, whether the value correspond to the sensing in this short range or in this long range, all right? Because in this way, you can also detect the presence of object which is very, very close to the sensor, all right? So it's up to you, okay? So this is the typical response from infrared sensor, all right? So, and the second solution is to use variable transistor. So variable transistor has a fiber. So then use the fiber to couple with linear position. For example, if an object could undergo linear position, you can couple this linear position with the linear position of the fiber. Then in this case, we can convert, okay, variation of the position to variation of resistance. Then we apply a voltage to the R circuit. Then variation of resistance will become variation of voltage, DC voltage, all right? Then equation is here, all right? So this one is coupled to the linear motion of a target object, all right? So this motion will produce a variable resistance at the output. This variable resistance will produce a corresponding output voltage because the current is equal to V input divided by the total resistance, okay? Then this current times this variable resistance is equal to the output voltage, all right? And this ratio actually is equal to the ratio between this distance and the total length of a transistor, all right? Resistor, all right? So this is the total length of a resistor. Then this is a variable length of a resistor, right? So you have this relationship. So this is for linear motion. Then how about the rotary motion? So we also have a rotary potentiometer or resistor, right? And the typical application is showing here. For example, when you design a human-sized robotic hand, then there are many degrees of freedom inside. Therefore, you cannot afford to use a big sensor to measure position. Then we may have this small-sized potentiometer, okay? And inside here, you will see there's a wiper. The wiper will undergo rotary motion, right? So you have a 2-pin as an input. Then let's say this is a common ground. Then this is the input voltage. Then this will be the output voltage. All right. So this is a very simple device. Then mathematics will looks like this. Okay. Then in this case, it's similarly, okay. So the current which will flow inside the resistor is equal to input voltage divided by the total resistance. Okay. Then output should be equal to the current times to the variable resistance R, and the variable resistance R. So that means the ratio between this one to this one should be equal to the ratio between the angular position, okay, angular position of the wiper divided by the total angular position of this circular resistor. By default, we assume this circular resistor cover 360 degrees, then we use a 2 pi, okay? If this one is smaller than 2 pi, then you use another value. But anyway, it does not matter because we have a calibration. Here we see an error because this is a systematic error. It's always fixed, all right? So it does not matter because through the calibration, we can cover this error, okay, or eliminate this error. So you can use this idea value for the entire range of this circular resistor, right? So the theta divided by 2 pi basically will give you the relative resistance as output, okay? Then output voltage is a function of angular position of the wiper, right? So this is an equation for you to use. Okay, so you see, okay, by using principle 1, so it's quite straightforward just for you to come out the solution for the module, which will transform position into DC voltage, right? Then how to apply the second principle? If let's say we want to use microcontroller as a sensor of a digital signal, right? Then in this case, we need to convert position into digital signal of either time series. Okay, later on we'll show you example. That means the position correspond to the number of pulse, okay, in series or parallel bit. So then in this case, so it corresponds to the spatial pulse. That means the B1, B2, B3, B4, Bn, okay? So that is a spatial pulse, right? So this is a time series of a pulse, and this is a spatial pulse, right? So anyway, these are digital signal, right? So then in this case, we can leverage on the use of a microcontroller, okay, to help us to come out the solution for the design of measurement and the sensing system for position, right? Then how to apply principle 2 to design digital measurement and the sensing system for position. So this slide basically show you the detail. So inside the microcontroller, actually we have a digital input output port, all right? And all these ports could take in digital signal, digital pulse, either in time series or in parallel bit, both, does not matter, right? And inside microcontroller, we have arithmetic and the logic unit plus counter counter include the hardware counter and the software counter, right? And inside microcontroller, they are programmable timer. That means the frequency and could be changed, and the counting value, like count up, count down, what is the maximum counting value could be changed, okay, could be set by the programmer. So it means the timer is programmable, all right? And of course, we have a digital display, okay, device which could be attached to the microcontroller, right? And here you will see the microcontroller could undertake serial counting, okay, pulse by pulse, or parallel counting. That means so you have a 8-bit or 16-bit or 32-bit, okay, spatial pulse at the input, then in a single cycle. So microcontroller should be able to read the value. All right. So therefore, now our focus should be on the conversion of a position into digital pulse. If we have a solution to convert the value of a position into digital pulse, either time series pulse or parallel bit, okay? So it should be good enough, all right? And here is a background information for you to know, okay? So pulse basically is just a square, but in this square, actually, there are 4 meaning or 4 event or 4 active signal. We use this technique term. For example, inside this pulse, we have indication of a level high, 5 watt, level low, 0 watt. That means 0, 1. And the transition from a low to high, we call it as a rising edge, and transition from high to low, that is a falling edge. So microcontrollers are able to make a distinction among these 4 events or 4 active signals. Therefore, you can tell the microcontroller response to rising edge, response to falling edge, response to level high, response to level low. So these are the background knowledge for you to know. All right. So actually, inside one pulse, there are these 4 pieces of meaningful information, and the microcontroller will make use of this meaningful information to undertake action. All right. So you will see microcontroller actually is a very, very sophisticated system. All right. And in addition, we have an input output. Then you will see the microcontroller could also issue a signal to trigger the start of doing measurement and the sensing, or stop of doing measurement and the sensing. So you see, so this is a very, very powerful device for you to use. All right. Now, okay, this is the blueprint. Okay. So now your focus is just to answer this question. Could you convert position into digital pulse or not? If answer is yes, then you just use a microcontroller to implement your measurement and the sensor system for position. All right. Okay. And this slide basically just give you confidence about the power of a microcontroller, right? And this is a drawing from our Cortex microcontroller. And here we just show you digital I/O interface. So you will see, and we have a digital I/O pad. I/O pad means, so in parallel, this one has a 6 port, okay? Each port has a pin. So you have a 6 port. You just imagine you have a 6 layer, all right? And each port, each layer will support a pin, A here, not 1, okay? So then you see you have a lot of controller. You use the register, okay? And you can control the, okay, this is the controller for the, and eventually you can trigger the action by external signal, etc. Okay, so this just basically help you to understand that the microcontroller is very sophisticated device. Okay, very, very powerful device. All right. Okay. Now we focus on this question of how to convert position into digital pulse. Do we have a solution? Okay, the answer is yes. Okay, for example, we use ultrasonic waveform to do the measurement. Okay, so we have emitter, transmitter, receiver. Transmitter just transmit out the ultrasonic waveform. Okay, when this waveform hit the target, then it will bounce back. Then the receiver will detect the angle from the ultrasonic waveform. Okay, therefore immediately you know. Okay, so we need to detect. Okay, the starting time of doing transmission and the stop time of after the reception, right? After the receive, okay, then what should be the stop time? Okay, because the hardware here, electronic circuit basically will output this information, and also this one will receive information about the receive a control signal about the start of doing measurement. All right, so more detailed solution is here. All right, so you see the interface between microcontroller and this ultrasonic sensor is like this. All right, so the microcontroller will issue a start pulse, tell it, okay, start to do the measurement. All right, then this one will return a digital pulse, square pulse, okay, and has a two important event, okay, or signal, active signal. One is a rising edge, another is a falling edge, okay, or rising edge, then falling edge. So we look at time direction in this way, okay. So T1, T2. So T1 corresponds to the rising edge, then tell the microcontroller to start the counting. Then this one will tell microcontroller to stop the counting. All right. So rising edge at T1 to start the counting, falling edge at T2 stop the counting. All right. Then based on the counting value, we should be able to calculate what should be the value of T2 minus T1. All right. Then for microwave, because this is a mechanical wave, okay. So in air at the normal temperature, more or less we know like its speed is 340 meter per second. Use this number, all right. So if you have other sensor which will tell you temperature and the humidity, so actually you can couple temperature sensor, humidity sensor, distance sensor together in order to obtain very precise calculation. Okay, if let's say we just want to know the rough indication about distance, so then we just use this number, 340 meter per second. Okay, so then use this formula, immediately we know what is the distance. Okay, divide by 2, basically the wave will travel is a round trip, okay, going from sensor to the target, then from target back to the sensor. So it's a round trip. So this is why we need to divide it by 2, right? So you know the solution of producing, okay, this pulse, and this pulse basically define the time window for doing the counting. That's it. All right. So it's very simple. Then how to convert position information into digital signal in parallel bit instead of a series of a bit. And this is a common popular solution in industry. All right. So we call it as an optical absolute encoder. And here, this video make use of a 3-bit to illustrate, but in practice, we may have a 10-bit, 12-bit. Okay, that should be the, or 14-bit in order to have a higher accuracy, right? But for educational purpose, we just use a 3-bit to help you to understand how it works, all right? But in practice, we must come out the design with a 10-bit, 12-bit, or 14-bit, all right? Okay.
Rotary absolute encoders consist of a translucent disc with a binary pattern etched on it. The pattern consists of a series of opaque and transparent slots. The slots are arranged in a concentric circular fashion. And the number of slot sets is the same as the number of photocells used in the encoder. A light source is located on one side of the strip, while photocell detectors are placed on the other side. The rotary absolute encoder shown here has 3 sets of slots and hence uses 3 photocells. As discussed earlier, with 3 photocells, an absolute encoder can detect 8 unique positions. In other words, the full shaft rotational angle of 360 degrees can be divided into 8 angular intervals of 45 degrees each that can be uniquely detected by the encoder. Here is another view of the 3-bit rotary encoder. If a more accurate measurement is needed, then an encoder with more data bits can be used. As discussed earlier, this means using more photocells in corresponding circular slot sets. Typical rotary absolute encoders have 8 or more photocells. The encoder disk shown here is from a rotary gray code 8-bit absolute encoder.
All right, so the video basically showing you 2 design solutions, one with a 3-bit, another one with a 8-bit, all right? But these are for illustration purpose, all right? So in practice, such a conversion may involve the use of 10-bit, 12-bit, or 14-bit, etc. All right, so and this slide basically showing you the scenario with 2-bit at the output. So from here, you will see we can put the output from these 2-bit together in order to form a parallel bit. Okay, so parallel bit correspond to one number, one value, digital value. All right, but of course, for individual bit, there is time series. But here the focus is on the spatial pulse. Okay, so basically it means a parallel bit. Okay, by combining all the output bit together. Okay, so this is with the 2-bit, then we can only measure 4 positions because 0, 0, 0, 1, 1, 0, 1, 1. It's just 4 indication of a position. All right, and how's about the 3-bit? So in the video, then we see the design solution which will output 3-bit data. Okay, so then in this case, 3-bit correspond to A position because 0, 0, 0 all the way to 1, 1, 1. Okay, so they are A combination, right? Then how's about the 4-bit? Then 4-bit will give you or give us 16 position. Okay, 0, 0, 0, 0, 1, 1, 1, 1. So in total, there are 16 positions. All right. Then you see the internal design is like this. All right. So we have 4 photo cell. Okay, by combining the output of these 4 photo cell, then we have 4-bit in parallel each time. And this could be the input to the microcontroller. Microcontroller can take in, but each port can take in 8-bit. With the 2-port, it can take in 16-bit. With a 4-port, microcontroller can take in 32-bit. Okay, so it's not a problem at all. But normally, for this type of a conversion, we use 14-bit. So 2-port is good enough. All right, so it's more than good enough to input 16-bit in total. Okay, at each time. All right, and then this is a solution with A photo cell. Okay, so with A photo cell, then we should be able to measure 256 position. All right. By combining the output from this A photo cell, then we have a spatial bit of 8-bit. All right. Then for each individual cell, it will come out its own time series. Okay, but here focus is look at the spatial pulse. All right. So it's a spatial combination of the digit. All right, or bit. Okay. And then this slide basically showing you a little bit of mathematics involved in the calibration of accuracy of the measurement. For example, if we use n-bit, to encode the output, so it means we have n photo cell, which will do the conversion of position into parallel bit. So each parallel the parallel bit has a combination, in total n bit. So then in this case, each value, okay, when we count the digital value, okay, correspond to this number, because once you rotate this we can call this as a pitch angle. So when the disk rotate one pitch angle, then only one bit here will change. All right. So then we can count the number of the bit change or something like that. All right. Then what should be the resolution? Because this corresponds to the pitch angle, then half of the pitch angle corresponds to the accuracy, plus minus, okay, angular position, all right? Then here is an example, all right? So let's say optical absolute encoder has a 4-bit output. If the counter's digital value is this one, okay, then what is measuring the angular position and its accuracy, all right? So because we have a 4-bit, then what will be the pitch angle? Okay, pitch angle is equal to 2 pi divided by 2 raised to the power 4, right? So then this corresponds to the value 4, right? So 4 times this one. So basically it will output this value, okay, 90 degree, it corresponds to this one. Then what is accuracy? Okay, so half of the pitch angle basically is the accuracy of this sensor. Right, so this is some physics or mathematics behind the conversion from position value into digital number, okay, or digital pulse. All right. Okay, so that's all for the solution. Okay, so basically you have two types of solution for you to do the conversion from the position into digital pulse. So you have the solution, then you just follow this one, then combine with the microcontroller, you should be able to come out with your design of a sensing and a measurement system for position. All right. So like for many other sensor, always remember to do calibration, especially when you apply the first principle to design the measurement and the sensing system for position, because the first method make use of the principle of converting position information into DC voltage, right? Then from DC voltage into digital number, all right? Then in that case, you have a YI output from microcontroller. Then this YI may not exactly correspond to the value of a position. So therefore, we need to do calibration. And the purpose of calibration is to make sure that the rectified value Z from YI is equal to XI. So therefore, XI, ZI will follow this relationship. Okay, so this is a straight line, which is 45 degrees above the horizontal axis. All right, so especially when you apply principle 1 to design measurement and the sensing system for position. If you apply the principle 2 to design measurement and the sensing system for position, normally you do not need to do calibration because everything is already precise. However, you can still do calibration here because in case, who knows, you may make a mistake inside your program or whatever, all right? Then in this case, this calibration allow you to rectify, okay, any error or any mistake, okay, during the sensing process, all right? So you can still do calibration when you apply principle 2 to come out the design of a measurement and the sensing system for position, all right? Once you have done the sensing module, once you have done the calibration module, then remember to do error analysis. So it means use your new sensor or measurement system to repeatedly take in the data. Then you calculate the mean value, standard deviation, maximum error, minimum error, and also to do the experiment when you increase the input and you take the data, and when you increase or decrease the input, you record another set of data, then you do the comparison. Then in this case, you will know whether there is a hysteresis error or not, okay? So always remember to do this common task, because the buyer or user of your sensor or measurement system may want to know this information, all right? And if you want to sell your product, you must tell the buyer about this information, all right? Okay. And for the measurement of the position, besides these two methods or two principles for the design of measurement and sensing of a position, we could also make use of a vision system to measure position in a two-dimensional space, and then measure position in a three-dimensional space, or measure position in a one-dimensional space, like in this case, all right? And we will study vision-based method in separate lecture, right? So this just for you to know, and you treat this slide as an announcement about the future lecture, which will teach you vision-based method for the measurement of position, all right? So that's all for today's lecture, okay? So the key takeaway is for you to understand the application with the information about the position, and also the basic detail related to the definition of a position. And also we have studied the way for us to do indirect measurement of the position. And also we have studied two principles which will guide you to come out the design solution of your own measurement and the sensing system for position. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.